Welcome. I want us to compare experimental probability with theoretical probability. In experimental probability, we will be kind of experimenting. So this is a chance for us to actually carry out the experiment and observe whatever outcomes we observe. Whereas in theoretical probability, we are using certain assumptions. For instance, given a die, which is fair, in other words, a die that is not biased, we know that there are 6 faces on a die with numbers 1, 2, 3, 4, 5 up to 6. Now, those numbers have an equal chance of actually showing when we roll a die. And so we say the probability that we shall get a 1 will be 1 out of 6 because there are 6 faces or 6 numbers, and any one of those numbers can actually show up. So when you roll, for instance, in theory, you roll a die, say 6 times, then you would expect theoretically to get 1, 1, 1, 2, a single 3, a single 4, a single 5, and a single 6. So each one of them can fall once each if you roll a die, say 6 times. That is in theory though. Because if you do roll a die 6 times in practice, you may not get a single 1 and a single 2 and a single 3 and a single 4 and a single 5 and a single 6. But theoretically, we are saying they should be evenly distributed. And so in theoretical probability, the probability of getting a 1 will be the same as the probability of getting a 2, same as probability of 3, same as probability of 4, of 5, and of 6, which is 1 over 6, which will actually give us 0.167. So that is theoretical probability. Now let's look at practice, experimental probability. Let's experiment and actually roll a die. So let's take a single die, roll it 6 times, and record the number of ones that are actually going to show up. And then here, I'm going to calculate the relative frequency. I've already put in the formulas. So the formulas are already in there. So in this case, we are saying the relative frequency of getting a 1 will be equal to the number of ones that we get divided by the number of rolls. So if we roll our die 6 times, then we shall check how many ones we get. So we take that number, the number of ones, and divide by 6. That will give us the relative frequency of a 1. Same for 2. How many 2s did we get out of the 6? That gives us a fraction or a decimal fraction, which is our relative frequency. Same for 3. How many 3s did we get out of the 6? So we shall do that and see what the experiment actually gives us. All right, so let's roll the die. I'll use a Geogebra Simulation. So I'll click there and get to that link where we are rolling dice. I want us to pick only one die. So let's pick one for now. And we're going to roll our die. So let's roll it 6 times and see what we get. We could either get a 1 or a 2 or a 3, a 4, a 5, or a 6. And so I'll start rolling. That's 1, 2, 3, 4, 5, 6. So to summarize that, after rolling this 6 times, you will notice we are getting 2 ones. Okay, there's 2 ones there and 2 2s, you see that? We did not get a 3, so it's 0 3s. We got a single 1, sorry, a single 4. We did not get a 5. And we got a single 6. So that is in practice. This is quite possible. So let's record that. I'll record it here. So after rolling the die 6 times, there was only there were 2 ones. And we get that 0.333 by dividing 2 by 6. Now, how many 2s did we get in our experiment? We also got 2. So we expect the probability, the relative frequency to be 0.33. How many 3s did we get? We got nothing. Right, how many 4s did we get? We got 1. And how many 5s? We got nothing. And how many 6s? We got 1. And so this is the picture after rolling the die 6 times. You will notice that the relative frequencies are not equal. All right. Let's continue and see if we can see a pattern. So I'll roll my die 300 times now. So this is 100. After rolling 100 times, this is what we get. That is 200 now, and that is 300 now. I need you to look at the bars. You will notice that right now the bars are not the same height. That is obvious because the number of times we are getting a 1 is different from the number of times we are getting a 2, a 3, a 4, a 5, and a 6. And so if those numbers are different, then the heights of the bars will also be different. So let's record that. So 56 ones, 39 twos, 43 threes, 62 fours, 52 fives, and 44 sixes. And look at the probabilities now. Let's try 900 times and see what happens. I'll reset this again and go 900 times. So that's 100, 2, 3, 4, 5, 6, 7, 8, 9. So after 900, these are the answers that we get. 133, 148, 157, 178. Okay, so these are the probabilities. Once again, that's the probability of getting a 1 there, a 2, a 3, a 4, a 5, a 6. So these are our relative frequencies. And yeah, they are not the same, but the question is, are they very different to each other? And how do they compare, for instance, with the probabilities that we got earlier? Notice that we are increasing the number of tosses or the number of rolls. So with 900 rolls, these are the numbers that we are getting. Do you think there is a trend that you see? Let's do this again 1,200 times. I'll reset that 1,200 times. 1, 2, 3, 7, 8, 9, 1,100. That is 1,200 times. Okay, let's copy down those numbers. So that's 194 there. That's 209, 196, another 196, then 201, and 204. Let's jump, maybe let's skip that to 6,000. Let's go to 6,000 to save time. 6,000, I'll reset. Then 6,000, how easy can I get there? Let's go in hundreds and get to 6,000. So I'm doing this 6,000 times. 6,000 times, let's see what happens. That's 6,000 times. 1026 for the 1, 1035 for the 2, 977 for the 3, 988 for the 4, 981 for the 5, and 993 for the 6. And there we are, guys. 0.171 for the 1s, that is the relative frequency. 0.173 for the 2s, 0.163, 0.165, 0.164, 0.166. All right, I think you will notice that the numbers are different, but maybe not very far from each other. Not quite far from each other. Right, to save our time, let's go to 30,000. Let's do that 30,000 times. I'll reset 30,000, I'll go in tens of thousands. So that's 10,000, that's 20,000, that is 30,000. Right, let me see if I can put those numbers down. 4945, then 5013, 4962, 4983, 5051, and 5046, 5046. Okay, so those are the probabilities. If we roll our die 30,000 times, that is 0,165 for the ones, 0,167 for the twos, 0,165 for the threes, 0,166, 0,168, 0,168. You will notice something now. The numbers are almost becoming the same. If I were to round off these numbers, actually, if I round them off to 2 decimal places, you will notice I'm getting the same answer, 0,17. Maybe let's do that. Let's round off to 2 decimal places. We will get 0,17, and you see now the numbers are kind of the same. That is not the case for the other numbers before that. So if we take the other numbers before that and we round off to 2 decimal places, I think you'll see the difference. You will see that those numbers are not the same. You see there is a difference. Of course, that there is 0,17, 0,17, 0,16, 16, 16, 17. But they are different. Go back there. Those numbers close to each other but different. But now we have a situation where almost all of them are the same. You see that? And so maybe finally, let's do this thing 1 million times and see what happens. 1 million times. Let's reset 1 million. That's 10,000, 20,000, 50,000, 70, 80,000, 90,000. Oops, 100,000. I would need to continue again. That's going to be quite a lot. Maybe let's stop here at 100,000. Right, we will enter those numbers there and see what happens. So let's change this now to 100,000. Okay. Then we have 16,795 ones. Then we have 16,612 twos, and we have 16,683 threes. We have 16,692 fours, then 16,684 fives, and 16,534 sixes. Okay, what do you notice now? You see, to 2 decimal places, we are getting the same answers. And if you look at the pattern right from up there, when the number of rolls was few, the probabilities or the theoretical, or rather the relative frequencies, were not quite the same. They were close to each other. But as we go down, you will notice we are getting the same answers. So now the question is, can you write down what you observe experimentally? What happens to the relative frequency if we increase the number of tosses? Can you compare the relative frequency to the theoretical probability? Our theoretical probability for each of these numbers, 1, 2, 3, 4, 5, and 6, is 0,167. Round off to 2 decimal places, that's 0,17. So what is the conclusion?